So our next speaker is Dr. Mujahid Abbas from University of Johannesburg, South Africa, and the title of the talk is Fixed Point of Multivalued Friendly Mappings. Dr. Abbas, you can continue.
First of all, thank you, Naisa, for your invitation and organizing committee as well for giving me an opportunity to discuss my work with great minds over here. Thank you, everyone. Thank you, everyone, for being around. As you know, the title of my talk is there in front of you. The plan and the outlines of my talk is basically I'll be discussing something about the background, then I will jump to the concept of friendly mappings. And that concept of friendly mapping was then extended to the concept of multi-valued friendly mapping. And finally, we will discuss if friendly contractions and if time allowed, time permitted, I will go towards the application. Otherwise, I will conclude my lecture at that point. Let's start with this quote. A friend in need is a friend indeed. So the concept of friendly mapping, its name was picked up based on this quote. And this appeared in one of my paper in 2022. And when this talk will develop, you will find the justification of the name of friendly mapping. Why are we calling it a friendly mapping? So let's start with this. Let me see if I can remove this slide over there because something is this. Just want to, yes, now it's okay. A topological space has a fixed point property if every continuous map, which is a self map on X, has a fixed point. Let me give you a very simple example. If you take set of all real numbers and I define a self map, which is a translation map, for instance, f of x equal to x plus 1, this map is continuous. But this continuous map does not have a fixed point property. So the moral of the story is the set of all real numbers does not possess fixed point property. And in a similar way, if you take a mapping F from S1 to S1, when I say S1, it simply means it is the boundary of a unit disk. And your mapping is such that it rotates each point on S1 through an angle of pi radian. This map is also a continuous map, but it does not have a fixed point. So there are different topological spaces which have fixed point properties, and there are some which don't. And it is also known that if you have two topological spaces which are homeomorphic, and if X has a fixed point property, then Y has a fixed point property. So in that sense, the fixed point property is topologically invariant. So this concept, the fixed point property of set equipped with some topological structure, has been extensively studied by Brouwer. And this is very well known Brouwer fixed point theorem, which says that every convex compact subset of a Euclidean space has a fixed point property. If I go to the one-dimensional case, I can simply say that if you have a mapping which is continuous and it is defined on a closed interval AB, taking values in the set of closed interval AB, then it has a fixed point. And this one-dimensional version of Brouwer fixed point theorem can be proved using intermediate value theorem. And if you go towards the two-dimensional version of Brouwer fixed point theorem, it can be used using two-dimensional non-retraction theorem. So keeping this in mind, we can say that if I prove this theorem on a closed interval -1 to 1, then every closed interval AB has a fixed point property because every closed interval AB is homeomorphic to -1, 1 closed interval. And in a similar way, if you look at set of all real number, your open interval is not homeomorphic to set of all real number, so your open interval does not have a fixed point property. So the next question is, it is really useful to study fixed point property of the set with respect to the family of mapping satisfying certain conditions rather than a restricted class of mappings. So here is the definition. We can formalize it in this way, that a non-empty set X is said to have a fixed point property with respect to the family this of mapping if you consider the collection of all mappings and F satisfies certain property, then this has a fixed point. This set has a fixed point. And we say X is a fixed point space with respect to that family. Now, when I say that F satisfies certain properties, it could be the class of non-expansive mapping, it could be the class of contraction mapping, it could be the class of strictly pseudo-contractor mapping, it could be anything. I mean, what I'm saying, you have a collection of mapping which satisfies certain property, and every element of this collection has a fixed point, and our space is said to have a fixed point space with respect to that family of mappings. This is very basic definition. We have a metric space, you have a mapping. It is said to be contraction if distance between Tx and Ty is less than or equal to some alpha multiplied with distance between x and y, where this alpha is coming from 0 closed, 1 open. It simply means, in a very simple terms, I can say that if you have some unit ball in a domain and this mapping acts at that unit ball and you go into the codomain, that unit ball will be contracted. It will not remain the same as it was in the domain of your mapping. So this is a sort of contraction mapping, and this name is very obvious. It will contract the given unit ball in the domain and transform some contracted version in its codomain. And you know that what is the fixed point theory? We have all been talking about it. We basically work on identifying the conditions on a mapping and on the set X which guarantees the existence of a fixed point. So the basic ingredient of the fixed point theory revolves around a class of mapping and the underlying structure of the mapping. And you need to study different conditions on mappings, as you would have seen that different mappings have been defined, like pseudo-contractor mappings and then non-expensive mapping, resolvent operators. So many class of mappings we deal with. And then we have a certain spaces. It could be a metric space, it could be a compact, it could be a Banach space where you don't have a structure of inner product. It could be Hilbert spaces and so many sets you have. So basically, what we take, we need to study certain conditions on the mapping F and on the underlying structure so that the existence of the fixed point is guaranteed. So this is Banach who proved this theorem, and if you look at the statement of this theorem, you will find two ingredients over here. One is a mapping, which is a contraction mapping. Other is a space, which is a complete metric space. If you have these two ingredients, the existence of the fixed point is guaranteed. Not only the existence of fixed point is guaranteed, but its uniqueness is always guaranteed. So because there are certain situations where you have infinitely many fixed points, such as if you take the identity mapping, which is a continuous, which is a non-expansive mapping, and you have infinitely many fixed points. In that case, there is a situation when you don't have any fixed point, but the ideal situation is you have a fixed point, it is a unique as well. The contribution of this Banach fixed point theorem is not only lying in the existence, but it really gives you a very simple iterative algorithm to approximate the fixed point. One of the most simplest iterative algorithm you can see in numerical analysis, and then there are many examples of such iterative algorithms, such as when you look at the Newton-Raphson method. So these all iterative algorithms are Picard in nature, which was suggested by Stephen Banach. So this is a Banach fixed point theorem, which I have already discussed. Now, suppose X and Y are two topological spaces such that X has a fixed point property, but Y does not possess the fixed point property. As I have already mentioned, that if these two spaces are homeomorphic and then X has a fixed point property, then Y possesses the fixed point property. So the question is it possible to construct the collection of the mappings from Y to itself such that Y is a fixed point space with respect to that collection of the mappings? The answer, we will be using a very simple commutative diagram to introduce the notion of friendly mapping, and then we will come back to these questions. Look at this very simple concept. Look at this commutative diagram. You have four sets, A, B, C, D. There is a path from A to B. There is a path from B to D. And then there is a path from A to C, and there is a path from C to D. So we have four paths in these sets. And these two paths which directly take you from set A to set D is, and then you have the path which take you directly from set A to set D. If the outcome of these two sets, the outcome of these two paths is same, this diagram is a commutative diagram. So you can find it is a like of a commutative mapping over here, H, F, and K, G. Not in the sense of uh, commutative in the class of, as the people have been discussing, the common fixed point theory. It is not given in that sense. But when we say that this diagram is commutative, it simply means that if you follow the path from A to D, or you follow the path from A to D that way, or you are coming through the set B, the outcomes are same. So this is here is the concept of then friendly mapping. You have two non-empty sets, you have a mapping from Y to Y. It is said to be friendly mapping with S, which is from X to S. If there exists a mapping U, look at if T U of X is same as U S of X. So if you look at this mapping, what I'm saying that we have two mappings, one is T, other is S. And then we are bringing another mapping U into the picture. How? We are saying that T acting at U is same as U acting at S with every X in the domains. So you can just think of this mapping U is a mapping which is linking these two mappings T and F, and you can call it a friendship. This mapping U is something which is a friendship between T and S. So these relations, you can see it pictorially as the following. So look, you have two mapping. One is S. It was a self-mapping from X to X. There was another mapping T, which was from Y to Y. And then you can see a mapping U, which is connecting X with Y, and a mapping U, which is connecting X with Y. And you move from X to Y with the help of two paths. First is U and other is T. And then again you move from X to Y following a different path. One path is S and other is U. And if their outcomes are same, you say your mapping T is a friendly mapping with mapping S. So I denote the collections of all friendly mappings like this. Now you will find this is very simple way of proving the existence of the fixed point. In that case, you have two non-empty set, you have a self-mapping on X such that the set of the fixed point of S is non-empty, mean one set has a non-empty fixed point set. If there is another mapping which is a friendly mapping with S, then fixed point of T is also non-empty. Fine. So if you look at this very basic structure, we are not requiring, any topological or metric structure on the underlying sets. We are not requiring any topological structure of the mapping as well. We are not requiring the continuity, non-expansiveness, contraction. We are simply saying that one mapping is friendly mapping with other, and if one set has a fixed point, then another set has also a fixed point. Proof is very simple. As T is a friendly mapping with S, there exists a mapping U from X to Y such that this happens. Since fixed point of set is not empty, then you can find some X star such that Sx star is equal to X star. And then using the concept of friendly mapping, you have T of Ux star, U of X star is equal to Ux star. And you can see that now Ux star will become the fixed point of T. So this means the fixed point of T is a non-empty. Before I move, I would just like to know from Maisa that those 5 minutes will be deducted from my talk, or I can go and I will complete my talk by 5:35.
No, you can't just continue. It will not be deducted from you, but still you are restricted within the 25 minutes.
Okay.
Yes.
Okay. Yes, because I was thinking as of those 5 minutes will be deducted from my talk. So
No,
if it
no,
is
no.
not the
It
case,
will not be deducted. You can continue. It will not be deducted. You will not
okay,
you will not get injustice.
okay,
Thank you. So
okay,
we are
okay,
5 minutes slow, right? We are late.
okay.
Yes, we have 5 minutes.
According to my watch, I have 10 minutes because it is 5:25 at my
Yes,
side.
yes,
Okay,
yes,
yeah,
yes.
continue.
I'm gonna close it by 5:35.
Okay.
Yes.
Okay, so giving at this, the question which I imposed at the start of my talk here is a corollary. You can find the answer that if x and y are two non-empty sets, if x has a fixed point property, then y has a fixed point property with respect to this class of collection of the mapping. This is very simple example, very undergrad level example, but you can see that if x is equal to r and y is equal to r square, you have two mapping. One is 10x minus 2, simply scaling it, scaling the identity mapping and then translating it. Then there is another mapping, say T of P, which is defined from r square to r square. Then this mapping T is friendly with S when u of x is taken to be this one. And you can easily see that this condition is satisfies that T of u of x is same as u of s of x. So these are the friendly mappings, and the mapping u that really plays the role of a friendship. That is something which connect the space from R to R square. Now I move towards uh, the second part of my talk where we discussed a multi-valued friendly mapping. When I say it is a multi-valued friendly mapping, it simply means that you have a mapping which acts on a set and gives you which act on a point and give you a set as the outcome, and its fixed point could be considered as x star belonging to T of x star, where 2x is the power set. And when we say the multi-valued friendly mapping, you can well imagine that the equality will be replaced with some sort of subset type of notations. We say that we have two multi-valued mapping. T is friendly with S if there exists a mapping U from X to Y, and you can see that this mapping is a single valued such that V of Sx is contained in T of Ux. And here you can see what do we mean by V of A. V of A mean the collection of all U of A when A is coming from A, where A is some subset of X. So here is the theorem which says that if you have two non-empty sets, S is a multi-valued mapping, its fixed point set is not empty. T is a multi-valued mapping which is friendly with the given mapping S. Then again, a fixed point of S is not empty, then fixed point of T is not empty. So here, at the least, you can get some feel that why we call it a friendly mapping. If your friend feels a pain, your friend, if your colleague feels a pain, your friend is also feeling that pain. If your friend has something, it is almost taken as a granted that you also possesses some kind of things like that. So you can get some feel regarding a concept of that friendly mapping. And here the proof, I'm going to skip it. I can share my slides and everyone can go through it. Very simple proof, which shows that the multi-valued mapping, one having a fixed point set non-empty, other mapping which is friendly with it also has a non-empty fixed point. And here is a very simple example which uh, shows you that the collections of all friendly mappings with the given mapping S is indeed a non-empty collection. And here is a mapping U, which plays the role of a friendship. So now here we come towards the final part of my talk where we are discussing the friendly contraction mapping. Uh, the question of whether condition 2 of theorem 1 can be replaced with another condition, the answer is affirmative, but the argument now becomes a little more subtle. We introduce the concept of a friendly contraction mapping. Now, when we talk about the friendly contraction mapping, we don't have anymore the facility of talking a set without any structure. Definitely, we need some structure, and that structure is very simple. We have a matrix space which induces, a host of topology. A mapping T is friendly contractions if these conditions hold. So you can now see the mapping T, and it is a friendly contraction with S if this condition is satisfied. So when I will be sharing my slides, you can see the contraction mapping was distance between Tx, Ty is less than or equal to, say, alpha distance between X and Y. And here you can see that what I'm saying is the distance of T of Ux as T of UW is less than or equal to distance Sx and Sw, and you are not finding some alpha over here. This is a sort of, you can get the feel of a non-expensive mapping over here, but it is not non-expensive indeed. So here is the example when we say T is not a friendly mapping with S. So theorem 1 is not applicable over here, but this is a friendly contraction. So we have seen that this mapping is not friendly to S, but friendly contraction as well. And here is the theorem 3, which talks about the friendly contractions with a continuous map. This this is another theorem which says that you have two matrix spaces. Mapping is friendly contraction with the continuous mapping this. If the fixed point set is not empty, then there will be a fixed point iteration scheme which will satisfy this property. And if it satisfies this property, then fixed point of T will be non-empty. So I close my talk at this point, and I invite, if you have any questions, I'll be very happy and I'll be very glad to respond. I cannot hear you.
Yeah.
I believe that you are saying something.
Thank you. Yeah, thank you so much for the great talk. Yeah, we appreciate you. And if you have any question, you can ask the speaker.
Stop recording.